Hello everyone, how you guys doing? Welcome to Midas Expert webinar and thank you for your time today. I'm Sunkyu from Midas and I'm the host for today's webinar. Today's webinar, Analysis and Design Prestress Segmental Crosshead to BS5400, is presented by Sanusi Muda. He has 27 years of design experience in bridge engineering and has participated in various major bridge projects in Malaysia. In today's presentation, he will talk about the concepts of segmental crosshead pier design, BS5400 design requirements, and application using Midas Civil. During the webinar, if you have any questions about the content, just type it in the question box in the control panel. We'll collect the questions and answer them after the session. You'll be able to get the answers via email. You can also write your questions after the session is done and send them to us by email. And if by any chance you miss some part of the webinar, please do not worry. We'll send out the link of the recorded webinar to your email and also the PowerPoint materials. Alright, thank you guys. This is it for the introduction, and now we're gonna get started. Enjoy the webinar.
Hi everyone, welcome to another session of Midas webinar. My name is Sanusi Muda. Today we are looking into case study design Prestress segmental crosshead to BS5400. The content of topic today, first I present about my case study involved of the project, one of the bridge project in Kuala Lumpur, and we go to the section properties and geometries, design load, construction sequence, analysis, crosshead design, SLS, and crosshead design, ULS. I was involved with some package of this project, and Midas Civil primarily used analysis and design of the bridge, anti-type pier, and the dash highway is a new expressway under construction. Currently, the entire length of 20 km built on bridge viaduct. Most of the piers are built on existing road, and the pier type must not obstruct the existing traffic flow below. Anti-type pier is the best option in this matter. T-shaped piers consist of single column with 30 meter width of cantilever cross beam adopted in most of the viaduct. This session I will show preparation for the design of PSC cross beam for the T-shaped piers that supporting a numbers TN beams. Showing here the construction of PSC segmental cross beam that is currently actually ongoing, and some have been finished. The bridge is a precast beam and in situ deck type supporting on the T-type pier. The span is 30 meter and the average pier height is about 20 meter. The bridge will carry out dual carriageway, and each direction is each direction of carriageway is 14 meter width. You can see here the T pier types consist of 5 numbers of precise concrete segmental crosshead pier that we will be going to see the design procedure of this type of pier. Material properties adopted is concrete grade 50 Newton mm square, modulus of elasticity EC equal 34 Newton mm square, and density 25 kilonewton cubic meter. Reinforcement we use steel grade Fy equal 460 Newton mm square, with modulus elasticity is 200 kilonewton mm² and standard density 78.5 kilonewton cubic meter. And the processing strength, we adopted ultimate strength 180 newton mm². This is the commonly available here, and must check local availability with the supplier of the strength, processing strength that we are going to use in the design. Next, section properties for this type of gear is consists of column, segment 1 that we have shown you before, segment 2R that is a tapered section, segment 3R is the cantilever section, and this left side segment 2L is a tapered section, and segment 3L is a cantilever typical section. And the section of column is a in-situ construction that will be made a composite with a pierhead construction. The average height about 20 meter. The size we adopt here 3.6 by 1.6 meter, and this is actually the biggest section for Crosshead. The total height is 4.2 meter. This dimension we will input in the design properties, in the analysis design properties. And this is a Crosshead. This section will be made composite with the column section. And this is a segment cantilever section. Actually, we have to modify it slightly, because if we're going to define the taper section, we must have the numbers of points to be defined of section within I, N, and Gn must be similar, but must be similar numbers. So in that case, I have to add another 5 mm to make it similar with In and Gn. Otherwise, the Midas will not generate the section. Okay, this is tapered element. Tapered element will be generated with Midas tapered functions. PSC design parameter adopted actually based on BS5400. The partial safety factors for materials at ultimate limit state, reinforcement and prestressing tendon 1.15 and concrete 1.5. Partial safety factors for materials at SLS based on method of stress distribution, whether 1.25, 1.67, for pre-tension 1.25 and post-tension 1.55. And design limit, stress limit adopted during at transfer and during construction for pre-tension 1 MPa and post-tension 1 MPa. At transfer, the flexural tensile stress in the concrete should not exceed the following values: 1 Newton mm² due solely to pre-stress and coexisting direct and temporary load during erection. And number 2, 0.45 square root FCI for pre-tension members, and 0.36 square root FCI for post-tension members due to all other load combination. The allowable stress will be input in the PSC design function in the Midas and will be compared with the stresses occurred during construction. The PSC design again, we still in PSC. The following outputs will be checked. Serviceability limit state is concrete stress limitation under service load. Number 2, concrete stress limitation at construction stage. 3, principal stress under service load. 4, principal stress at construction stage. Then 5, tensile stress for pre-stressing steel. At ultimate limit state, we will check bend resistance, shear resistance, and torsional resistance. This check will be carried out with design feature in Midas. This is the book of reference that can be referred. And this book is Prestress Concrete Bridge Design and Construction by Nigel R. Hewson. And ultimate ULS will be carried out by Midas, and material factor here we will be input in the Midas design feature. The loading consists of permanent load, imposed load, and traffic loads. The loads will be combined in construction stages and final load combination. The dead load consists of precast beam and deck stack and diaphragm. For superimposed dead load, RAPEC and services and also surfacing are considered. The life load will be according to BS5400 based on carriageway width 14 meter. National length is 4 numbers, and the national wind width will be 3.5 meter. Highway loading HA, HB30 and HB45 combination are required. The project requirement for traffic loading is to comply with following load combination: SLS combination 1 type HA loading for pre-stress design class 1, or SLS combination 2 to 5 type HA or HA in combination with HB30 to pre-stress design class 2. For alternate limit state combination 1 to 5 type HA or HA in combination with 45 are required. The wind load has been determined in accordance with BD 37/01, adopting a basic hourly mean wind speed based on Malaysian MS 1553 2002. Temperature load ranging from 38 degrees Celsius to minimum of 15 degrees Celsius. Mean temperature adopted 26.5 degrees Celsius. Traction or braking will be according to BS37 based on the max load length. The maximum traction braking is 750 kilometers and will be distributed along the load length. The scaling nominal load of 300 kN point load is applied on landing community and transversely to get the most severe load effects. The loading of the village analysis will be extracted and tabulated for input in Prestress segment peer loading. Based on inspection, combination 1 to 3 will be the most critical for peer design. These are the loading which have been obtained from the village analysis. for beam 1 to beam 8 consists of span 1 and span 2. The following is the beam positions for point loads in Midas Civil. The position will be input in the point load cases. The analysis in the Midas will be carried out for construction stages with time-dependent effects and prestress loading effects and nominal loads, which are obtained from the village model. Now we are going to input the data in the Midas Civil, and we will make new files for analysis, and we're going to specify the material. First, we have to make sure what unit we are going to use, and now we go to the properties tab and select material properties, and in the pop-up box click add for material data import grade 50 for concrete, and select standard USRC and input the grade 50 concrete and apply. And now we're going to add prestressing steel properties. The steel will be based on ASTM as based on the availability of the material in the local market. The most common material for prestressing material here. Next, add properties for in situ concrete. Also use grade 50. Next. Now we are going to define the section properties of column, and the column. So we're going to use the built-in section properties, and select view the user and input the column and input the size we require, h equal to 2.6, b 1.6, and apply. For segment 1, this one we need to select PSC, otherwise the design PSC will not be performed. So important to select PSC. Select PSC value because we're going to import the properties. Properties can be defined in coordinate here or import using SPC section properties calculator available within the Midas Civil. Okay, next. So we have to define the parameter for design, T1, T2, BT, and HT. This will be used for shear design. And the position of the shear check. And here we specify the section based on center top. Again, define segmenting out. Repeat the similar process. Next, we have to specify parameter for design T1, T2, BT and HT, and change offset, and here we interrupt center top. All section we will use center top offset. For segment 3L, again we repeat the process. Next, this is section 3L. Section 3L actually similar with section 3R. And now we have to define the tapered section. So we select the tapered section, the tapered. Two sections are required to be defined in tapered section. The section at IN and JN. So we select the section for each end. And next at the JN, and we have to change the offset. So taper segment for segment 2L, this is the size I. Segment 2L for J, and change the offset. And next, the time dependent material. First we have to define the clip and shrinkage at the material. We use CAD FIP material, and we input the characteristic compressive strength of concrete based on 28 days age. And next we are going to specify the compressive strength of material, and here specify grade 50, and we use 58,000 kilonewton meter square, and click the draw graph. Now we're going to specify material link. So we select the clip and shrinkage to link with compression 50, and we select the 50. Here we click add modify. We add here. Next. The next step is definition of geometry of the structure. Next. Now we're going to create the nodes for the models. Here the position of the node and the coordinate of the node to be input in the model. And now we're going to define the element of the structure. You can select create element and select properties, and have to select the type of section and the coordinate for the element. This is done for section 3L, for segment 3L. Next, we define the segment 2L. Segment 2L is a tapered section. The tapered property we have assigned previously. We have defined in the section, the intersection properties. So now we're going to assign to the element. Now we're going to assign segment 1. Next, segment 2R for the right section, and lastly segment 3R. Now the crosshead section is completed, and next we're going to define column element. Now column element, we have defined the element here, and next step is boundary condition for the structure. Define support and select the support group. Have been defined in the group section, and select the fixity of the support. Okay, now we define the temporary support for the construction stage. Temporary support construction stage now completed. This one for the 3R section. Because the process is very big, we're not going to add extra load on the pier. We have to define this by elastic link. So step 4, loading. Now we are going to define the static load cases, and in the static load cases table here, we are going to fill all the construction stages load cases that we're going to analyze, and also all the load that will be carried out on the bridge during the services. Now we are going to define dead load for the pier, and these are typical how we define the typical concentrated load on the element. And we have several points load, concentrated load to be defined, and here is the distance. We have to define absolute distance of the loading. The distance has been provided in the previous PowerPoint. This is the overall loading that has been specified for the structure. Now we're going to specify the prestress load. Select the temperature and prestress load buttons. In the prestress load button, we select tendon properties, and we define the properties based on the our design kernel, but this one can be revised according to the our design output. Next is standard prestress load. In the standard prestress load, we were going to assign the tendons according to the load group. Load group we must define based on construction stage. So these tendons will be analyzed based on the loading group. So number one, select the group. This is the column 1, here is the group. And 2, select the tendon to be included in the group. This is the column 2 tendon. And 3, the stress load or force on the tendon. This is column 2. And click Add. And we will apply this one by one. We will repeat this process one by one for the all tendon. Next, we are going to define the tendon profiles. Click Add. Here is the input for tendon profile. You input tendon name here and select property and the elements to be assigned. And in this structure, we have two numbers of C1, and the coordinate we have to be input here, and this is the distance from the top. That's why I like to specify the segment based on center top. Easy to check the position of tendons. Here I defined the crosshead, and the coordinate start from 0 and below is the column. In this way, I can easily check or modify when required the coordinate of tendon. If I started the column from 0, and it's quite difficult to check and revise. Maybe it takes a longer time compared to this method. Next. Here is the profile of the tendons used in this used on the structure, and we will repeat the previous step using this coordinate. Here is the tendons profile. Now we are going to see the construction stage. Here is the detailed construction stage for the PSC crosshead. So this one has been carried out during construction. This is a stage of tendon stressing and span launching, all to be considered until all the tendon have been stressed. So we can check the activation of the element during construction stage in group activations, and here here is the time of each of the element is activated during construction stage. Example here, column activated during the beginning of stage 1 and followed by other elements. So we also can check the boundary activation during construction stage, and some of the boundary condition to be deactivated, such as temporary support here at certain stage to be deactivated. And also we can check the activation stage for each of the loading we have been specified during construction. This is how we are going to define construction stage. We can define by generate, and here I use construction stage generations and stage 1 to 23, and it will automatically generate all the stages. Here we are going to select which one to be activated during each stage of construction. This is the typical stage I selected, and the remaining is to be done one by one. Altogether 23 stages, and I am not going to show all here because the time is limited. This is the order loading I have generated based on the schedule provided in the presentation before. Okay, all the element. So this is the loading, shown here. And step 6 is the analysis. In the analysis, I select the load requirement for combination based on BS5400. And this is the load combinations. The load combination will be used for checking the stressors, allowable stressors, and bending moments, also used for design stage later. This is the result obtained for construction stage. The result shows that all elements are in compression and no tension here, and compression within the limits. This one for the result for the top construction stage, for the top at the top. This one result during services. That's result during services. Also, we can check the tendon losses. We click the tendon loss graph and we obtain how much the losses for each stage of construction. And finally, we go to the design stages. The design will be carried out in accordance to BS5400, and in preference we have to select the BS5400 design code. Otherwise, the unit will not consistent with the BS5400. To carry out the design, we have to specify reinforcement for each of the element required in the design. In this case, I will provide the reinforcement for all the segment crosshead, and reinforcement, longitudinal reinforcement and with shear reinforcement must be defined in section manager. Select section manager and the reinforcement have to be defined in here. This is the shear reinforcement definition, and this is the reinforcement for segment 3R. This is the shear reinforcement for 3R. So that the definition of the reinforcement has been defined. Actually, we need to reanalyze again. After analysis, we go to the PSC design. In PSC, we select BS5400 and we select the design parameters. We specify the allowable stress limits during SLS, also during construction stage, and we select the output that are required in our design. Next, we have to specify the grade of concrete in accordance to BS code, and in order to carry out the design, we have to specify the position of the elements. Maybe we do not need to select all, depend on our requirements. Next, the output that are required for our design, the severity of the environments to be considered in the design based on the S5400 requirements. And next, we have to select the load cases to be considered in the design. And now we can perform the design. After perform design, we can check all the design requirements such as fractional strength, shear strength, combined shear and torsion strength, stress during construction, stress during service loads, and all the design elements that are required. And the good thing of Midas, it will check all the section that we have specified, and this is really helps in our design. It will really helps to speed up the design process and detail. And that's all for today. Thank you very much for attending this session. Thank you.
Alright, I think this is it for today. I think it was a great opportunity to learn about pre-stressed segmented crosshead. I hope the audience have felt the same. If there's anyone who didn't have a chance to ask questions during the session, please feel free to email us at midasbridge@midasit.com. Also, like I said earlier, we'll send the recorded webinar and PPT file to your email. So thank you everyone who came today, and have a good day. Bye-bye.